I am subtracting first row. So you get minus 2, then 3, then 1 minus 1, 0, 0, so on. Last also 0. Then third row minus first row. So minus 2 again. 1 minus 3. So 0, 1, minus 2, 0, then 5 minus 1. So 4, then 0, and so on, 0. Now again minus 2, then 0, 0, then you get 4, 6 minus 1, so 5, and then 0, 0, and so on. Last is also 1 minus 2, 0, 0, 0, 0, so on, and here you get n. So many terms now we have simplified. Now how to get the value of this determinant? For that, what I do, I take columns, second, third, fourth, these are columns. Now these are rows and these are columns. Now in the first column, this is C1, this is C2, and so on. This is these are columns. Now from in the first column I am adding 2 upon j plus 1 Cj, where j varies from 2 to n. So in the first column I am adding jth column multiply by 2 upon j plus 1. So what happens if I take second column? So if I take j equal to 2, then here what you get? 2 upon 3, second column you are adding. So when you add this, what do you get? Here 3 plus 2 upon 3 times 1 added. Now here what happens? 3 and here 2 upon 3. So 3 cancel. So minus 2 plus 2. So this gets 0. Then third column you are adding. So what you get? J is 3. So 2 upon 3 plus 1, 4. So 4 upon 4, 4 will go. So when you add, this will become 0. And here you will add 2 by 4. 1, 2 by 4, then 2 by 5, and so on and so forth. 2 by n. And other terms remains as they are in the first row. Second, in the first column, second element is 0, third element is 0, and so on and so forth. All elements in the first column except the first one. This is the first element of the first row. Now all are 0. Now here what do you get? 3, then 0, 0, so on, 0, then here 0, 4, 0, and so on. Okay. So n continues this. Here 0, 0, 5, 0, and so on and so forth. So 0, then here 0, 0, 0. Last term is n. Now this is the simplification of a very complicated determinant or determinant of the matrix. Now here if you observe, this is first element. Now first column, except the first element all are zeros. Now in the second column, from third onwards all 0. Here second onwards 0, here third onwards 0, here fourth onwards 0, here fifth onwards 0, and so on. So if I take this now, this one up to this, so you get a lower triangular which is everywhere 0. So in this case, as a matrix, this is a upper triangular matrix. So for upper triangular matrix, now all the elements below the principal diagonal are 0. Such matrix are called upper triangular matrix, and for that upper triangular matrix, the value of the determinant is nothing but the product of the diagonal elements. Because if you expand with the first column, this times this determinant, then 0, 0, 0. So everything goes 0. Then when you take this one, everything is 0. So it is just a product of diagonal elements. So if I denote this by dn, we have already denoted. So dn is nothing but 3 plus 2 by 3 plus 2 by 4 plus so on, plus 2 by n into this product. So this is first element, then 3, 4, 5, so on, n. So this is the value of the determinant. Now here 3, 4, 5, n. Now so if I multiply each term, let me multiply each term. Now if I multiply this term, so then you get 2, 3, 4, 5, n. 1 you can write. So it is 1, 2, 3, 4, 5, n. So numerator is n factorial. So if I take n factorial common, so from this is n factorial upon n. So n factorial I have taken, so I will write this way. So first term is n. Now just one term before it is 2 upon n minus 1. Now if I take the product, it is 2, 3, 4, 5, and here n minus 1. So n factorial you have taken common, so 1 upon n minus 1, and so on and so forth. So in that case, here you get 1 upon 4, then 1 upon 3, then 1 upon here this you can write as 1 plus 2, and when you take n factorial common, you get this equal to 1 plus 1 half. Okay. So value of the determinant, this determinant, okay, value of this determinant, the given determinant, is n factorial into the bracket 1 upon n plus 1 upon n minus 1, so on, 1 upon 4 plus 1 upon 3 plus 1 upon 2 plus 1, which can be written as, this was the original determinant, very complicated determinant, but by simple properties of elementary matrices and determinant, we reach to the value dn as dn, the value of the determinant, as n factorial into. Now I will write this way. So 1 first, then 1 half, then 1 upon 3, and 1 upon 4, and so on and so forth. Last is 1 upon last but 1 and last. So this gives dn upon n factorial is 1 plus 1 half plus 1 upon 3, 1 upon 4, and so on and so forth, 1 upon n. So, if I take this sequence dn upon n factorial, this sequence, that is same as this sequence, na? 1 plus 1 half, 1 plus 1 upon 3 and so on, 1 upon n, this sequence. But we know this is harmonic sequence, na? Nth partial sum of the series sigma 1 upon n, and we have already shown that this is a divergent series. Harmonic series is divergent, na? It tends to plus infinity. So, this sequence, na, diverges to plus infinity. So, this set, if I take this set dn upon n factorial, where n is greater than or equal to 2, then this, where dn is this one, dn is our this one, 3 1 1 etc. So, this is not bounded because this tends to infinity. So, this is not a bounded set, or as a sequence this is a divergent sequence. This sequence as a sequence, it is a divergent sequence. So, this is a very interesting applications of harmonic series. Let me take some more results. Let me take the graph of the function f x equal to 1 upon x. If you draw a graph, it is like this. F x equal to 1 upon x, x positive, x positive. Now, I'll write this as figure 1. So, if I take this as n, then n plus 1, n plus 2 and so on. Here 2n minus 1 and 2n. Now, there are two ways. Now, if I take this one, now what is, let me take 1 upon n plus 1, 1 upon n, 1 upon n plus 2 and so on and so forth up to 2n minus 1. Now, look at this rectangles, this height. No? So, it is the value of this power, coordinates of these points are n and 1 upon n. So, this can be written as 1 upon n into n plus 1 minus n. So, into 1 is, you can write as n plus 1 minus n, 1 upon n plus 1, n plus 2 minus n plus 1 and so on and so forth. Okay. 1 upon 2n minus 1, 2n minus 2n minus 1. So, these are the sum of the areas, no? The sum of the areas of the rectangles. On the interval n to 2n. Now, this area is definitely greater than this area, which is bounded by this curve, the vertical line segments x equal to n, this is x equal to n, and this is x equal to 2n, x axis. So, this will be greater than the area, and this area, this area is nothing but definite integral from n to 2n 1 upon x, the graph is 1 upon x dx. So, that gives 1 upon x is log x, 2n n. So, that is log 2n minus log n, that is equal to log 2n upon n, that is log 2. That means this sum 1 upon n plus 1 upon n plus 1, 1 upon n plus 2, 1 upon n minus 1 is greater than log 2. And instead of that, if I consider these rectangles, then their sum will be less than this area, and in that case, because taking here, so in that case 1 upon n plus 1, 1 upon n plus 2, so on up to 1 upon 2n, that will be less than log 2. So, you have upper sum and lower sum, and log 2 is sandwiched between them, and as number of intervals increases when n tends to infinity, this increases, this decreases, and that gives the logarithm 2. So, here